Okay, I guess we should get started. Welcome back from the break. And now for something completely different. Sitan is going to talk about learning deep ReLU networks. So go ahead. We can't see your slides though. Take your time. Yep, we can see them now. But you're muted.
Can you hear me now?
There we go. It's all yours.
Nice. All right, excellent. Great, so I'm happy to talk about joint work today with Adam Clivens and Raghu Mecca on the question of learning deep ReLU networks. Okay. So at a high level, the motivation for this talk is the age-old question of packed learning. So given labeled examples from some distribution, you would like to output some predictor f hat that achieves low test error on the original distribution. Okay, so the practitioner's tool of choice for this particular question would be simply to run SGD to train a large deep neural network on these examples and use that as the predictor. Okay, so it's no secret that this works great on real-world data. And a central mystery in the theory of deep learning that's been the focus of a ton of work over the last few years is why this seems to work so well in practice. Not only from an optimization perspective, but from the generalization perspective that we focus on. Okay. Right, so the first question you can ask is, why does SGD seem to work so well in practice? But apart from asking what's so great about this particular algorithm or family of algorithms, you can also just ask the broader question of why real-world data seems to allow us to evade well-known worst-case hardness results for learning neural networks. And so in that spirit, you could ask a second question, which is, for which distributions D is this particular task tractable for any polynomial time algorithm, not just SGD? Okay, so these two questions are clearly related on a spiritual level and on a technical level. And I would argue that they, at their core, get at a much more ambitious agenda, which is to design more principled, ideally provable algorithms for this particular problem that outperform existing techniques on any number of axes, like speed, sample efficiency, robustness, what have you. Okay, so in this talk, I'm going to focus on question 2. And specifically, I'm going to focus on an instantiation of question 2 that's been well studied in recent years. And that's the question of learning a teacher network. Okay, so we're going to assume that the labels yi actually come from some unknown neural network f. Okay, so just going to focus on the realizable case in this talk. Great. Okay, so what is a neural network? So we'll focus on this particular concept class of feed-forward networks. So specifically, we have some collection of weight matrices, W1 through WL. And more succinctly, you could write this resulting function as follows. Okay, and right, so how this function computes an output, a scalar output y, is that you take your d-dimensional vector x, and you left multiply it by some weight matrix, pass it through an entry-wise ReLU function, left multiply by weight matrix, etc. Okay, and at the output layer, we have just a single vector, which computes an inner product between that vector and the vector of activations up to that point. Okay, and the output is some scalar value y. Okay, so some parameters of interest for this question are the ambient dimension d, which we should think of as extremely large. We should also, let's also define L to be the depth of the network, which I've defined here to be the number of weight matrices. Let's let the size denote the total number of columns across all of these weight matrices. Okay, so it's the sum of the k sub i's from 1 to L minus 1. Okay. So an important parameter in this entire setup is a notion of effective dimension. So let me motivate that a bit. So a feed-forward network you can think of as not just a function from d dimensions to 1 dimension, but really a function that maps points inside the span of the columns of W1 transpose to points in R. Okay. So in particular, this function only really depends on the projection of x to the column span of W1 transpose. And all components orthogonal to it don't affect the activations of the first layer. And for that reason, because I'm interested in the column span of W1 transpose, I'm going to define the so-called effective dimension, K, to be the rank. Okay, and in this talk, we're going to think of K as being much smaller than the ambient dimension. And in fact, we're going to think of the overall size of the network as being much smaller as well. Okay. So any questions about the setup? All right, great. Okay, so this is the concept class we'll be working with. And we're interested in just the following basic pack learning question. Given labeled examples where the xi's are drawn from some possibly known distribution d sub x, and the labels are simply the output of this neural network when evaluated on a particular x, our goal is to output a network G, which is close to F in L2. Okay. All right, so that's the goal. And in this work, we're going to focus on the standard setting where the distribution over covariates is fairly benign. Namely, we'll assume that d sub x is standard Gaussian d dimensions.
Oh, Sitan, Ilias wants to know already why you're not solving an even harder problem.
Oh, sorry. Where is the?
There's noise added to the.
Let me look at the chat. Ah, good. Yeah. So it'll become evident when I talk about the techniques that we can handle sort of benign noise, but for simplicity, I'm going to focus on the realizable case. Yeah, and that's how the paper is structured. But we believe that this Gaussian noise shouldn't be too much of a problem. But yeah, it's a good question. So yeah, just for this talk, let's focus on just the noiseless case. Great. Okay. All right, so good. So now let me give a brief overview of some of the prior approaches. And I want to give a bit of a flavor of what kinds of techniques go into showing these results. Okay, so the question of learning ReLU networks has had an extensive line of work in past few years. And at least in the Gaussian case, all works focus on the depth at most 2 case. All right, so this is the picture I showed in previous slides, specialized to L equals 2. And you can think of F as being written in this more compact form, where you have a linear combination of ReLUs of inner products of the input with various vectors. Okay. And so this might be a bit of an oversimplification, so I apologize if I omitted some works. But at a very high level, I think of these existing results on learning depth 2 networks as sort of falling into 3 categories. The first are results that essentially use some form of spectral or tensor method, stemming from what amounts basically to Stein's lemma. The second category are techniques based on kernel methods, and the third category are algorithms that analyze the dynamics of gradient descent, either from a local convergence perspective or a global one. Okay, so the second category is somewhat orthogonal to the thrust of this work, in that they make the assumption that the inputs are bounded in norm, but as a result, they're able to handle much more general distributional assumptions as long as the inputs are supported in the unit sphere, or unit ball. Okay, so we'll primarily focus on 1 and 3, which apply to the Gaussian case. And it's safe to say that all of these results essentially need to assume some combination of the following 2 assumptions. The first being that the lambda i's, these coefficients which you should think of as the entries of the final vector W2. So the assumption is these are positive. And other works make the assumption that the WI's, which are the column vectors of W1 transpose, are essentially nearly orthogonal. So you can think of it as just that the condition number of W1 is good. Okay, so now let's, so I'm going to focus on the Stein's lemma and gradient method based results. But before I get into the details of that, let me just mention briefly that one reason why existing results have focused on this particular set of assumptions, or any set of assumptions at all, is that the goal has been a bit different than the goal of pack learning in this talk. Namely, most of the existing works have focused on parameter learning. Okay, so why do you need to make extra assumptions in the setting of parameter learning? Well, it's not hard to see that you can cook up sets of neural networks that have different architectures and weight matrices, but which all give rise to the same function. Okay, so here's a very silly example. All right, so if I take a neuron, I subtract it from itself, it's going to compute the zero function. And you can cook up slightly more sophisticated examples. Okay, so if your goal is parameter learning, namely to actually, given samples, output a network whose parameters are close to the true ones, you had better make some assumptions in order to guarantee that the parameters of the true network are uniquely identifiable from samples. Okay? And a very common assumption in this vein would then be to assume something like a condition number bound for the weight matrices. Okay? The point I want to make is that such assumptions are not a priori necessary for pack learning ReLU networks. Okay, so now let's give a sense for how these existing results leverage this kind of condition number bound assumption or the positivity assumption. And I'll start with techniques based on spectral tensor methods. Okay, so at a high level, these results use just the following fact, the following property for Gaussian distributions, which is that if I take the expectation of y times x, and x is Gaussian and y is computed by f, then this is equal to the expected gradient of f, evaluated over the Gaussian. Okay, and for one hidden layer, I can evaluate this explicitly. This is going to be some linear combination of the weight vectors wi. Okay, and this sometimes goes by the name of degree 1 Chow parameters. Okay, and you can take this one step further. You could look at degree 2 Chow parameters, and you could form the matrix expectation of y times xx transpose minus identity, and this gives you back the expected Hessian. And this is then going to be some linear combination of rank 1 matrices, projectors to the spans of wi's. Okay. And you can take this to its logical conclusion, and at degree m, there is some tensor valued function called the mth score function, so that if you form this statistic, it gives you back the mth derivative tensor of f. And then you can compute this, and this is going to be some linear combination of tensor powers of wi. Okay, and this is the specific form for the score function. Okay, so the details of this aren't super important, but what I want to emphasize is that all of these statistics involve computing some expectation of a product of y with a function of x. Okay, so that's the main takeaway. Now, how do these results leverage this kind of these objects? Okay, so if you assume that the weight matrix in the first layer is well conditioned, then morally the wi's are nearly orthogonal, and then you can just run your favorite tensor decomposition algorithm on the m equals 3 tensor and recover the parameters uniquely. Okay. On the other hand, if I don't assume that my weight vectors are well conditioned, and I'm happy to do just pack learning, then a recent work of Diakonikolas, Kane, Kotonis, and Zarifis showed that you can do something using the m equals 2 object. Okay. So why are lambda i's being positive helpful? You can show that the resulting b sub I coefficients here are positive. And so intuitively, you're not getting any kinds of cancellations. In particular, the resulting matrix y times xx transpose minus identity is going to be a sum of rank 1 matrices. Right? And the point is that in this case, because it's a sum of rank 1 matrices, the span of the weight vectors wi, you can recover from the top k singular subspace of M. Okay, so you've already recovered sort of the hidden subspace on which your function depends by looking at the SVD of this matrix M. And once you have this relatively small dimensional subspace, you can hope to exhaustively enumerate over it. Okay, so this will incur some exponential in k. And recently, another work of Diakonikolas and Kane used a much more sophisticated variant of this technique involving sort of the tensor generalization of this m equals 2 matrix. And they managed to drive the dependence on k down to quasi-polynomial. Okay, but anyways, the main takeaway from the slide should be that all of these sort of interact with the distribution via expectation of y times some function of x. Okay, now let's move on to the next technique. So I'm not going to describe in detail how the analysis works in these results, but let me just say something very simple, which is that if you want to do gradient descent with respect to the square loss, this is what your gradient update will look like for one hidden layer. And the point is that I can write this in such a way that I have two terms. One term, which is again some kind of expectation over y times a function of x, and then some expectation over a function which is purely depending on x. Okay, so this thing, I know the underlying distribution over x's, so I can in principle evaluate this explicitly. And all of the action is really going on in this statistic. Okay, and let me mention, this is for square loss, and there are some really nice works that look at modifying the loss function to make the optimization landscape more benign. But suffice it to say that all of the existing works that use gradient methods for this problem still need to use updates of this general form, and only apply in the case where the lambda i's are positive and the wi's are well conditioned. And the reason is that really the analysis goes into showing convergence in parameter distance. Okay, so this brings up the natural question: can we pack learn without assuming either of these assumptions? Okay. And so very recently, two groups of researchers showed that there's actually a fundamental barrier to answering this particular question. And the key insight that they made was this point that I've been sort of hammering repeatedly, which is that all of the approaches I've described so far could have been implemented not with samples, but just with an oracle that can answer queries of the following form. I give the oracle some function from d dimensions to 1 dimension, and the oracle spits out a noisy estimate of expectation of y times g of x. Okay, and so it was shown recently by Goyle et al. And Diaconicoulis et al. That any algorithm that only interacts with your underlying distribution in this fashion can't hope to learn general two-layer ReLU networks, even to constant error, without making roughly d to the size number of queries. Okay. So this is a pretty strong no-go result that rules out the kinds of approaches I've described in the previous slides. And so the focus of this work is really, of this current talk, is going to be, can you produce any polynomial time algorithm that can learn general two-layer ReLU networks in time less than this lower bound? Okay. And the other question we're gonna tackle is, can we finally hope to go beyond depth 2? Okay, so these are the main questions. Are there any questions from the audience before I continue? Okay, great. Right, so now let me tell you about the results before going into the techniques. Okay, so before I describe our results, here's just a picture of the concept class we're interested in again, and I'll keep this box of relevant parameters up on the top right. Okay, so our main result, or at least a baby version of it, is that for any depth L ReLU network for which the weight matrices are bounded in an operator norm, or specifically that the product of the operator norms is bounded by some parameter b, then we can properly pack learn capital F to error epsilon with the following sample complexity and runtime guarantees. So the sample complexity is going to scale just linearly in the ambient dimension, and it has some extra exponentially large term that depends on the error and these various parameters. Okay. On the other hand, the runtime, so let me just to remind you, K here is the effective dimension. So you should think of it as the rank of the first weight matrix. B is this operator norm bound, which naively could scale exponentially in the number of layers. Epsilon is the target error, and S is the size of the network, which is some dimension independent thing. Okay, the runtime looks similar. So we need a nearly quadratic dependence on the ambient dimension. And this sort of fixed parameter tractable term is going to be what we had here raised to the s squared power. Okay, and so, like I said, like B here could, feasibly just be exponential in the depth, right? If my operator norm is bounded by a constant at each layer, this could be, 2 to the L. And so one thing we would like to avoid is some kind of exponential dependence, doubly exponential dependence on the number of layers. And so we give sort of a compromise that says, if I additionally assume that my ReLU network is Lipschitz, which is definitely the case for any of the lower bound instances against CSQ that I described earlier, then you can hope to do better as follows. So note that capital B is always a naive upper bound on the Lipschitzness of the network. But in fact, I can now replace any appearance of B in my upper bound with a lambda at a very mild cost. Okay, so I can replace the B with the lambda, and I incur some extra log term that depends on this scaling factor B. Okay. Okay, so now you might be complaining that there is some strange dependence on the Lipschitzness, which doesn't appear in sort of existing techniques, in existing results for depth 2. And I would like to point out that actually, even for depth 2, in the presence of lambda i's, which are of arbitrary sign, you need at least some dependence on lambda to get some kind of scale invariant guarantee. Okay, so I'm happy to describe this more in the Q&A session, but I'll just state this as a given for now. Okay, great. So, but the main point I want to make is that these results go beyond the CSQ lower bounds that I described, and you can think of it as the first example of a neural network class that can be learned efficiently. For if you treat the parameters here as constants, but it's a class that can't be learned efficiently via noisy gradient descent. In particular, the CSQ lower bounds earlier would say that you need runtime scaling exponentially in the say k, with the base in that exponent being the ambient dimension. Okay, so we're avoiding this kind of d to the k runtime. Okay, I'll pause for questions. All right, great. So now let me say a bit about the results, or sorry, about the techniques. Okay, and at a high level, the key technical challenge is identifying the so-called relevant subspace for the underlying function. Okay, so what do I mean by that? So recall that when we think of the effective dimension k as being much less than d, then in essence, the function that we're trying to learn only depends on a small dimensional space of the input. Okay, so in particular, for any input x, f of x is exactly equal to f evaluated on the projection of x to the row span of w1. Okay, and so how could I try to get access to the row span? So one approach based on Stein's lemma would be to look at the matrix y times x6 transpose minus identity. And one consequence of these CSQ lower bounds is that this matrix can actually be 0 for general ReLU networks. Okay, in particular, this is true for the CSQ lower bound instances in those works. Okay, so what is a sort of simple way to get around this issue? Well, it would be to look at slightly non-SQ queries, non-CSQ queries. Okay, so let's consider the matrix, which is given by phi of y times x6 transpose minus identity for a carefully chosen function phi. Right, so it's still not hard to see that for any choice of phi, for which capital M is defined, the kernel of this matrix is still going to contain the sort of irrelevant directions, which I'll denote by U perp, the orthogonal complement in the ambient space of U. Okay, so how do you see this? Let's look at the quadratic form evaluated at V. Okay, this splits up by independence, right? So the point is that V inner product x is independent of pi ux because V is orthogonal to U. Okay, so I can split this up into the blue term and the green term. And let's say V is a unit vector. So this is nothing more than expectation over a univariate Gaussian gamma of gamma squared minus 1. Okay, and this integrates to 0. Okay, so this is super standard. And in a sense, this is the only place where we really need properties of the Gaussian as opposed to some well-spreadness conditions for a more general distributional assumption. Okay, so this is very standard. This is just saying that if I want to look at this matrix M, and I know for sure that if I find an interesting eigenvector of this matrix that's outside of the kernel, it will definitely be inside of the relevant subspace. Okay, but of course the hard part is ensuring that this matrix is non-zero to begin with. I'd really like to say that the inner product of my matrix with the projector to the relevant subspace is non-negligible. So let's write down this trace inner product. Right, this is just the right-hand side. And the key difficulty in the analysis is handling this minus k term. Right? You can imagine if my phi function were non-negative, and I didn't have this minus k here, well, this is going to be some expectation over a positive function, and I'm going to get some positive inner product, and I'll be in good shape to recover a single direction. Okay, so how do we handle this minus k term? Well, let's imagine I could produce some function phi which satisfied the following three properties. First of all, let's just ensure that this phi is non-negative for all inputs. Let's constrain it to not be identically zero when evaluated over different choices of f of x. This is just to ensure that the thing we're integrating isn't actually identically zero. And of course, we'll need some quantitative version of this later. Okay, and so the third and most important property that we're going to work with is the following constraint. Namely, I want that phi of f of x is non-zero only if the norm of the projection of x to the relevant subspace is large. Okay, so the contrapositive is if the norm of the projection is small, I want to make sure that phi of f of x is zero. Okay, so here's a picture of a nice choice of phi. For any choice of x for which the norm of the projection is small, phi of f of x is going to be zero. And only past this point am I going to start seeing some non-zero things. Okay, so this is what I want out of my phi function. And why would I be done in this case? Let's take this trace inner product and let's just split up according to the indicator of the following event. Okay, my x is either going to have large projection to the relevant subspace or small projection. So I'm just splitting up one into the indicator of two complementary events. Okay, and the point is that by property 3, the second term is going to be 0. For any x for which the projection is small, I'm constraining phi of f of x to be 0 by the contrapositive. Okay, so the second term vanishes just by design. And I'm just left with the first term. And now, note that this quantity here, if I constrain the projection to be large, this quantity is just at least k. And because phi here is non-negative, there are no cancellations, so we can just lower bound this by k times the indicator times phi of f of x. And finally, by property 2, I ensure that this guy is going to be not identically 0. Okay, so if I could ensure that phi satisfies properties 1, 2, and 3, then I would ensure that if I had infinite samples, and I took and I could estimate capital M perfectly and take its top eigenvector, it would lie squarely inside the relevant subspace U, and I would make progress. Okay. Cool. So how do we design such a phi? Here's a very simple choice of phi that would work. Take phi to just be the following threshold function. So on inputs z, for which the absolute value of z is small, phi is going to output 0. And for z, for which the absolute value is large, it's going to output 1. Okay, and I'll justify this choice of threshold tau in the next few slides. Okay, so before, the cartoon that we had for what phi should look like was something like this. And under this choice of phi, we're going to get something that looks more like a step function. Okay, so at some point, once the norm is sufficiently large, it's going to transition from having a response which is too small to having a response which is at least tau. Okay. And let me just say that this is reminiscent of a well-known technique of sliced inverse regression, where you essentially want to condition your data only on the xy's for which y is within a certain range, in the hope that the conditional distribution on x is going to look non-Gaussian in the directions that you're interested in, namely in this relevant subspace U. And so the key challenge is to sort of make this kind of technique quantitative. And this sort of approach was used in previous work joint with Raghu Meka to learn a different concept class called low-rank polynomials. Okay, so let's just see if I plug in this particular choice of phi, what does the trace inner product calculation from the previous slides look like? Okay, so here's just what I had on the previous slides. Let me move the k outside. And I claim that this actually simplifies significantly because of property 3. Right? The point is that if phi of f of x were 1, namely if f of x were sufficiently large in absolute value, then by property 3 I know that this indicator will hold, that this indicator will output 1. Okay? So in other words, I can just rewrite this expectation as the expectation of phi of f of x, which is just the expectation of the indicator that f of x is sufficiently large. Okay, and then this is just a probability. Right? So the trace inner product that we want to lower bound in a quantitative sense is really the probability that my response, y, is sufficiently large in absolute value. Okay, so that will be the sort of quantitative version of bullet point 2 that we'll talk about. So I haven't proven for you yet that for this particular choice of tau, properties 2 and 3 go through. But let me just give you a cartoon that will sort of convince you that this is completely reasonable. Right, so here is a heat map for, I think, a 2-layer neural network, just in 2 dimensions. Think of the relevant subspace as just R2. Okay, and for simplicity, it's kind of discretized. So let's think of each color as like a level set instead of as like some kind of continuous range. Okay. Okay, so the ball of interest is this ball of x's whose projection is too small. And I want to pick tau so that if my response is bigger than tau in absolute value, I'm guaranteed that I'm outside of this ball. Okay, so it's easy to design such a tau. Let me just take the maximum value of my network over any input that comes from this ball. Okay, and tautologically, if I see a point whose response is bigger than that, I know it has to come from outside of the ball. Okay, and so this picture kind of suggests that the answer to this should be, sorry, I can't see my cursor. This picture suggests the answer should be that I take tau to be effectively like this deep blue color, or like the value corresponding to that. So if I condition on my data being bigger than that, whatever value this color blue corresponds to, it's like I'm conditioning on the following like portion of my covariate distribution. Okay, so I'm just filtering out all points for which y is sufficiently small in absolute value, and I'm left with the stuff in purple. And this trace inner product that I care about is simply the probability mass of this purple region. Okay, so this is all just sort of like a cartoon to give you a sense for why it's very reasonable that I can try to design a threshold for which all of this works out. Let me just prove it, because the proof is quite simple. Okay, so why for this choice of tau can I satisfy property 3, for instance, namely that f of x is big in absolute value only if the projection is large. Okay, let's show the contrapositive. So let's say the projection is small, and I want to show that f of x is small. Okay, this is just a straightforward consequence of Lipschitzness. So if I take my f of x, recall that f of x only depends on the projection of x to pi of u. So this is the first step. And now by Lipschitzness, this quantity is at most the value of f at 0, absolute valued, plus Lipschitz parameter times the norm of pi ux. Okay. And now f of 0, remember this is a homogeneous neural network. There are no bias terms. So this is simply 0. Right? So this is, and I'm assuming that pi ux has bounded norm, and so I get the final inequality. Okay, so I'm done. So property 3 holds. This is not too bad. Okay, a slightly more involved calculation comes with proving step 2. So I'll just give you a high-level idea of this. Okay, so recall that the thing I wanted to show quantitatively wasn't just that phi of f of x is not identically 0. I really want to show that that the probability that f of x is large is large. Okay, in other words, I want to show some kind of anti-concentration for this function f. Okay, and so the proof idea is as follows. I'm going to exploit piecewise linearity of my network. Okay. So if the network has a non-negligible second moment, in other words, if expectation of y squared is non-negligible, then on average over the pieces of f, the linear pieces of f that you can see in these cells demarcated by white, a linear piece is going to have some variance and therefore some level of anti-concentration. Okay. For each of these linear pieces, it's not too bad to try to lower bound this anti-concentration probability. And in fact, you can lower bound it by a convex function in the variance, conditional variance in that linear piece. Okay. And why is it important that this lower bound is convex? This is so you can apply Jensen's and law of total variance. Okay. So if on average the variance of a linear piece is large, Jensen's is going to tell me that the anti-concentration probability overall is going to be large. Okay, so that's a very high-level description of the proof. Let me just summarize with the punchline. So this tells me that if my network has some reasonable amount of variance, and I pick my threshold appropriately, then if I condition my data on points whose absolute value is sufficiently large, and I look at the conditional covariance, then I'm going to discern from that covariance an interesting direction, namely a vector inside of capital U. Okay. And because the top eigenvalue has some non-negligible value, this means that if I form an empirical estimate of my matrix using enough samples and compute the top eigenvector, it's going to be close to the subspace I care about. Okay. And so you could be even more ambitious and ask, well, if I just took the full spectrum of M, all of the non-zero eigenvectors of M, could I hope to recover just the full subspace? And it seems like empirically this isn't necessarily true for certain choices of F. And in particular, if you test this on the CSQ instance, I think one of Adam's students found that you might be able to recover one direction, but you're definitely not going to recover the full relevant subspace U. Okay, so the million-dollar question is, how do you recurse? We found one direction. How do you find the remaining directions inside of this relevant subspace? Okay, and I claim that with a simple fix to this whole thresholding scheme, a lot of the analysis from the previous slides, you can actually pattern match to get the remaining directions in the subspace. Okay. So now let me talk about that. So our goal is to find the remaining directions inside of U. We found some vector v, and we'd like to find another vector v prime, which is orthogonal to v and inside of U. Okay, I think I see a question in the Q&A, but I can't access it. The span of nabla fx as x varies, or more algorithmically. Okay, so the question is, another way to get the relevant subspace is by taking the span of nabla f of x as x varies, or more algorithmically, sort of like the expected projector to the gradient at a point. Do you know how this compares to your estimator? Yeah, it's a good question. My instinct is that this, it's conceivable this kind of thing you could try out on depth 2, but yeah, it's not clear to me how the analysis will go for larger depth, but yeah, it's definitely something like an alternate approach. I don't have anything sort of substance to say about this, but it's a good question. I'll have to think about it offline. Okay, good. So so let's go back to finding the rest of the relevant directions. Okay, so this was the matrix that we considered in the previous slides. So one sort of silly way to try to avoid finding the same vector again, this vector v, would be to add projectors to the orthogonal complement on left and right. Okay, this is kind of silly. Like if this worked, if I could show that the top eigenvector of this matrix was some new relevant direction, v prime, I could have just made that same argument about the original matrix. Okay, so what kind of modification do I need? I'm going to modify this part of the definition of the matrix. So instead of thresholding on the response, I'm going to threshold on essentially the residual. Okay, so let's consider the residual computed as the absolute difference between the true response and the response that would have been calculated if I took my input, projected it in the direction of v, and put it through f. So of course I don't actually have access to this object. And I'll talk about this in later slides, but for now let's pretend we have access to this object. Okay, so it's still easy to see that the kernel of this matrix is going to contain the relevant subspace's orthogonal complement as before, and it's also by design going to contain the span of V. Okay, and that's just because we added these orthogonal projectors. And as before, the hard part is just to lower bound this trace inner product. Okay, so let's just write that out. Okay, so previously, how did we handle this kind of term? Let me just reproduce the slides from before summarized. And let me now show you how to sort of edit this whole argument to make the analysis still go through for finding subsequent directions. Okay, so let me just recall that you can rewrite this trace inner product as a probability. Okay, so the first modification is to the definition of M. Okay, so now the trace inner product we care about is this thing I showed on the previous slide. So how do these two properties that I want change? So the first property, instead of the probability that absolute value of y is large being large, I want the probability that the residual being large is large. The second property I want, before it was that the response is large only if the projection was large. And now I want that the residual is large only if the projection is large. And because I've projected away the span of V, I only care about x which are orthogonal to V. Okay, and finally, so the trace inner product, instead of being lower bounded by this probability that the response is large, it's going to be lower bounded by the probability that the residual is large. Okay, so far I've just pattern matched and things are fine. Now let me see how to handle properties 1 and 2. Okay, so property 2, I want to show that the residual is large only if the projection is large. So let's take any x which is orthogonal to V. And I would like to show that if the projection is small, then the residual is small. And this is just going to be by Lipschitzness again. So f of x minus f of pi v of x. I can first rewrite f of x as f of pi ux. And by Lipschitzness, I can upper bound this by lambda times the norm of the difference, which is going to be pi of the projection of x to the orthogonal complement of v inside of u. Okay, and I've assumed that this projection is small to begin with, so again I can upper bound this by lambda times root 2k minus 2. Okay, so property 2 is going to hold if I pick my threshold to be this value, lambda times root 2k minus 2. Okay, so this is very similar to what happened in finding the first direction. And similarly for this anti-concentration result, we can make the following argument that's also reminiscent of the previous slides. So it's just a simple win-win argument. Either the unexplained variance is large. In other words, I can't explain all of the variance using just this one direction v. In this case, the sort of residual function, f of x minus f of pi v of x, it's still piecewise linear, so we can just apply the argument from earlier. Okay, sorry about that. Okay, and then the other case is if the unexplained variance is small, well in that case we've already won. If I had access to this object f of pi v of x, and this L2 distance between y and f pi vx were small, then I could just output f pi vx, and I'd be done. I would have pack learned the underlying network. Okay, so that's the high-level overview for how this argument works. Okay, and to summarize, what this gives us is that if we found some collection of directions so far inside of the relevant subspace, and I called their span v, then the claim is I can find something that is orthogonal to v and still inside of u, as long as there's still some leftover variance. Okay, so this is saying if I form this matrix M prime, which filters y's based on the magnitude of the residual, and I look at the resulting covariance of the x's, this is going to have kernel, which is inside this irrelevant subspace, u perp direct sum v. In particular, the top eigenvalue is going to be bounded away from 0. So if I take the top eigenvector of M prime, I'm going to find a new direction, which is orthogonal to capital V, and still lies squarely inside of U. Okay, so that's the sort of infinite sample idealized calculation if I also had access to this f of pi vx at every step. I just iteratively run this until I recover the full relevant subspace, or I've terminated with a function that's close enough in L2 to the true network. Okay, so there's one complication to this, which is, of course, that I don't know this particular function. But I do know this vector space V, right? These are the directions I've found so far. And particular V is going to be some small dimensional subspace. So in particular, f of pi Vx is just going to be some small ReLU network over a known subspace. And so the idea is just to net over possible networks that are functions of V. Okay, so I'm just going to exhaustively enumerate over this net. Another issue is that you can only ensure that the directions that you found so far are close to a subspace V. First, because you only have finitely many samples, and second of all, because you have some error from netting over networks. Okay, and so the key technical complication is to understand like how stable is this entire argument with respect to these kinds of imperfections. And so the key technical step is to understand the stability of affine threshold functions of ReLU networks. So what do I mean by this? So let me now go to the key stability result. So really all I mean by stability of affine thresholds of networks is that if I take some ReLU network and I slightly modify its parameters to get something that looks slightly different, and now I want to compute some threshold function. Maybe I want to compute the threshold that dictates, whether something is bigger than this value corresponding to this dark blue color or less than that value. Well, if I sort of walk between these two networks, this area computed by this threshold is going to differ slightly. So now if I superimpose these two networks, really all I want to upper bound is the Gaussian volume of this area of disagreement, where in one network I'm in the dark blue region and in the other I am not. Okay. Right? And so in math, what this means is if I have two ReLU networks with, let's say, with the same architecture and whose weight matrices are close in operator norm, then the probability that the absolute value of f of x being large for one network and small for the other is small. Okay, good. So let me remind you, this capital B here is the product of the operator norms of the weight matrices. And how should I interpret alpha? In the course of our algorithm, I'm going to try invoking this on alpha, which essentially scales with the granularity of the net over networks that I'm working with. And I want to pick the granularity of that net to scale with the subspace distance between the span of the directions I found so far and the relevant subspace. Okay, and let me emphasize that really we care about the dependence on alpha here being linear, essentially because we need to, a priori, we need to iterate this whole argument k times. I find a direction, I iterate to find a new direction, and what I want to avoid is some kind of buildup in the exponent. So if I only had a bound that scaled with, say, alpha to the 0.99, this would yield sample complexity naively that would have to scale doubly exponentially in k. Okay, so let me give like a 10,000-foot overview of how to prove this lemma. And so one key takeaway that I hope you have from listening to this talk is the following very nice fact, proven by Ovchinnikov in the early 2000s. So basically the whole argument's going to boil down to some kind of hybrid argument on, you can think of some kind of depth reduced network. So I take any continuous piecewise linear function, and according to this result of Ovchinnikov, you can rewrite it as a depth 2 max-min formula. So think of this as like a CNF, but instead of and or gates, you have max and min gates, and the leaves are linear functions in the input. Okay, so really we'll need to open up the black box for this result for technical reasons that I won't get into. But at a high level, this is like the workhorse behind our stability analysis. So how do we use this to prove our lemma? So here's the lemma again. And the proof idea is essentially just a hybrid argument. Let's look at the max-min representations for these two ReLU networks, and let's call them phi and phi prime. Now let me open up the black box of the Ovchinnikov result and essentially argue that these should actually have the same clause structure. Okay, and once I have that in place, it's very clear what the sort of sequence of intermediate max-min formulas that I should interpolate along should be. Consider the following sequence of hybrids between these two formulas. At every step, I'm going to interchange one of the leaves at the top with one of the leaves at the bottom. Okay, so I'm going to replace U1 inner product X with W1 inner product X to form the first hybrid, etc. Okay, so I can interpolate just by swapping out leaves, and eventually I'm going to end up with another copy of phi prime. Okay, so I won't get into the details of this, but the whole point is that if you compare consecutive pairs of hybrids, then actually showing this disagreement probability bound in the lemma boils down to showing stability not of thresholds of ReLU networks, but simply thresholds of linear functions. Okay, and that's just an elementary estimate. Okay, so that's essentially the whole proof for the stability argument. Let me just conclude by sort of summarizing what the algorithm looks like. Okay, so here's the whole algorithm. You start off with a list of vectors that's empty, and this is going to be sort of the list of vectors that I accumulate, which I guarantee to be close in the relevant subspace over time. Okay, and I'm going to repeatedly do the following. Let's let V be the span of the vectors we found so far. I'm going to net over all networks over this span. If I encounter some network in this net which achieves low square loss, I'm done. And I can empirically estimate the square loss. So if this is the case, I'll just output the network. Otherwise, if that's not the case, I could still try forming this thresholded PCA kind of matrix, which again, I threshold based on the residual, where instead of the true F, I'm going to look at this F hat. Okay, and the point is that if V were exactly a subspace of U, and I found some interesting eigenvalue of this matrix, it's guaranteed to be within the relevant subspace. I won't have found some kind of dud. Okay, and the way I check whether the vector I found is not some spurious thing is just to check whether the eigenvalue of that vector is sufficiently large. Okay. So in the case where the spectral norm of my matrix is sufficiently large, I've sort of succeeded in this epoch. So I'm going to take that eigenvector that I found, I'm going to add it to my list. And by the preceding analysis, this ensures that I found something that's in the relevant subspace or close to it. And then I'll just repeat. I'll keep running this, and at every step I'm going to encounter more vectors to add into my list. And finally, at some point, I'm going to hit the first bullet point in step B, and I'm going to find that my vector, or my network that I've learned actually achieves low square loss. And at this point, I'm just going to output the resulting network. Okay, so that's the full algorithm. So now let me just conclude with a brief summary, and I'll leave on the slides a set of open questions. Okay, so the summary is that it was known that CSQ algorithms like noisy gradient descent and these kinds of spectral and tensor initialization procedures based on Stein's lemma fail to learn general two-layer ReLU networks over Gaussian inputs. And we got around this barrier by instead working with slightly non-CSQ statistics of the form phi of y minus f of x times g of x. Okay. In the process, we gave an algorithm which is fixed parameter tractable, although with an exponential dependence on the error epsilon, for learning general ReLU networks of arbitrary depth over Gaussian inputs. Good. Okay, so in terms of open questions, there are plenty. The most obvious one is, of course, to improve the dependence on all of the parameters that aren't the ambient dimension. Some other questions you could ask that might be sort of related in spirit are, could you get some kind of local convergence guarantee? Namely, use the whole procedure in this algorithm as some kind of spectral initialization, and then run some kind of iterative method to refine your estimate. In light of the CSQ lower bounds, this turns out to be a bit complicated, so it's not clear that this is possible, at least with gradient descent on square loss. Okay. Another question, of course, is can you go beyond the standard Gaussianity assumption? And like I said, we really crucially used Gaussianity to argue that all the matrices we've been working with, their kernel contains the irrelevant directions. But a lot of these anti-concentration arguments you can imagine with some extra work still applying to log concave distributions, for instance. So another sort of open secret in this literature is that these results are primarily tailored to the setting where you don't have bias terms. And we really heavily exploited that in the arguments in this talk, namely the homogeneity of the function computed by the network. And once you introduce the bias terms, it's no longer clear how to make any progress. Ironically, our arguments are very successful for ReLU activations and less successful for sigmoid activations. And crucially, it seems like we're definitely using the piecewise linearity of the ReLU activation, but we're also very crucially using its unboundedness. So another direction to push on would be to try to go beyond exploiting that so heavily. Okay, and the last question is maybe right now we're seeing exorbitant sample complexity dependence on the size of the network and the effective dimension. But this is essentially because we're picking a rather pessimistic choice of tau in order to ensure that we provably find a new direction. But you could hope to evaluate this kind of slice inverse regression empirically on these kinds of networks and see what happens. And this might inform smarter analyses for this kind of thresholding argument. So I'm sure there are plenty of other open questions that I'm happy to just discuss in the Q&A or offline. But for now, thanks for listening.
Great job. Any questions for Sitan? I mean, I feel kind of weird asking a question about my own work, so I'm not going to. So let's stop here. Thanks again, Sitan, for a terrific talk.
Thanks.
And we'll meet again tomorrow for a day primarily on graphical models. So we'll see you then. Thank you.
Thanks.